Programmable logic array. Programmable logic array consists of programmable AND array and programmable OR array. Inputs are given to programmable AND array and outputs are taken from the programmable OR array. We need to remember these points while constructing a programmable logic array. The array of AND gates are programmed to generate any product term of the input variables. The product terms are then connected to OR gates to provide the sum of products, SOPs. Output is inverted when the XOR input is connected to 1, since X exclusive or 1 equals X complement. Same way, X exclusive or 0 is equal to X. Therefore, if it is connected to 0, there is no change. We need to construct the programming table. These are the steps to construct a programming table. First, we need to list the product terms numerically. Then, we need to specify the required path between inputs and AND gates. Then, we need to specify the paths between the AND and OR gates. And for each output variable, we may have a true or a complement for programming the XOR gate. Let's try to implement a programmable logic array. For the expression F1 equals AB complement plus AC plus A complement BC complement. This is in the true form, which means it is not in the complement form. When you see F2 is equal to AC plus BC the whole complement, which means F2 is in the complement form. How to construct the PLA programming table? We shall see there are the product terms. So in each expression there are product terms. Let's see how many product terms are there in F1. 1, 2, 3. So there are 3 product terms in F1 and only 2 product terms in F2. So since this is a programmable logic array, we can write the product terms as total product term 1, 2, 3, 4 because the product term AC is repeated twice. So it is sufficient for me to write only once. Okay. So totally I have got only 4 product terms, namely AB complement, AC, BC, A complement, BC complement. So I am numerically representing it as 1, 2, 3 and 4. Now we need to find the inputs. The variables for these functions are A, B and C. So I have got the inputs as A, B, C, which are the variables, and the functions outputs F1 and F2. They are in the true form. Just now we saw F1 is in the true form and F2 is in the complement form. So I have represented that also here. And now we need to mention this 1, 0 blank. How did we obtain this? Let us take the first term AB complement. For AB complement, if the variable is present in the true form, I need to mention it as 1. A is present in the true form, so A takes the value 1. If it is in the true form, we have to give it the value as 1. If it is in the complement form, it has to be mentioned as 0, and if the variable is missing, I have to mention it as blank. So AB complement, A is 1, B complement, so B is 0 and C is not at all there in this product term, so C is a blank. Similarly, let us see the fourth term A complement, B, C complement. A is in the complement form, so 0. B is in the true form, say 1. C is in the complement form, so 0. Now we will see F1 and F2. How to represent for F1? What are the terms that are present in F1? First we will check the first product term, AB complement. So AB complement is present in F1. Therefore, I mark it as 1. AC is also present in F1, so I mark it as 1. BC is not present in F1, so I mark it as blank. A complement, BC complement is present in F1, so I mark it as 1. Similarly, we can do it for F2. Now, we shall see the diagram. So, how to see this diagram? Here we can see A, B, C are the variables. We can represent using the buffer, tri-state buffer. So, the complements and the true form, we are representing it here. So, we are getting A complement, B complement, C complement are the inputs to these AND gates. Here we can see the AND gates and the OR gates both are programmable. So, what are the inputs for the first AND gate? It is AB complement. So, I consider these two cross. So, whenever I put a cross mark, it means those inputs are considered. The remain, whenever we do not put a cross mark in this line, it means those those lines are not considered. So this is going to be your input to this AND gate, and we get the output as AB complement. Now when we want AC, AC is the second product term. So to have your AC as the second product term, we have to take the input from A. So this is your A, and next the input is from C. So this is your C. So we get the output as AC. Next we shall consider the third AND gate. For the third AND gate, the product term output is going to be BC. So for C, this is your C and this is your BC. So these are the inputs to the third AND gate. Then for A complement, B, C complement, A complement, B and C complement. These are the inputs for the fourth gate. Now we have to connect it for F1, F2. So since F1 is in the true form and F2 is in the complement form, we need to use an XOR gate. So here let us see what are the inputs for the OR gate first. This is the programmable OR array. So for the first function F1, we have these one. That is, we have the first, second and the fourth product term. So first, second and fourth product term. For F2, we have the product term as the second and third. So you can see here only second and third. So second and third product term. So these are the inputs. Now, just now we saw F1 is in the true form. So I have to connect it to 0 so that F1 exclusive or 0 will give me F1. Whereas I want F2 is in the complement form. So I need to get F2 complement. For that, whatever is available, I am going to complement it with 1, exclusive OR with 1. So it will become F2. So this is my F1 which is in the true form and F2 in the complement form. Let us also try to design and implement the two functions with a PLA. F1 and F2 are represented using sum of minterms. So using the K-map, we can obtain the expressions for this F1 equal to AB plus AC, and from this we can try to draw the expressions. We have got F1 equal to AB plus AC plus BC the whole complement, and F2 equal to AB plus AC plus A complement, B complement, C complement. So from here we can understand F1 is in the complement form, F1 is in the complement form and F2 is in the true form. So this is the programming table. We can see there are 1, 2, 3 and AB plus AC is repeated. AB plus AC is repeated. So we need not write it once again. And so this will be our fourth product term. So 1, 2, 3, 4. 1, 2, 3, 4 are the four product terms. Then we need to write if the variable is available as true form, variable is available as true form, I'll have to mark it as 1. If the variable is available as a complement form, I have to mark it as 0. And if the variable is missing, I should mark it as blank. We should not forget this. And if the entire variable for F1, you can see the entire expression is in the complement form. So I have represented as complement. Output is in the complement form. For F2, the entire variable is in the true form. There is no complement of it. So I mention it as true form. So same way just now as we did it earlier for the previous problem, same way we need to connect the inputs A, B and C. And so using the tri-state buffer, we will get the input lines as A complement, B complement, C complement. Then we'll have a programmable AND array and a programmable OR array. So whichever product terms we are including for those particular gates, we will include it. And finally, we'll have to include exclusive OR gate to obtain the final expression F1 and F2. Thank you.